May your day be filled with peace and blessings. Exploring parabolic transformations in a 60-degree mathematical context. In the realm of 60-degree math, equilateral triangles play a crucial role as the primary geometric unit. These triangles feature internal angles of 60 degrees, forming hexagonal lattices that serve as the foundation for symmetry concepts. While traditional Euclidean transformations like translations, rotations, and scaling still hold value, the focus shifts toward symmetry operations involving angles of 60, 120, and 180 degrees. Hexagonal symmetry takes center stage in this context, presenting a unique challenge when applying these concepts to shapes like parabolas which naturally follow quadratic curves rather than linear angular structures. When we delve into the transformation of parabolas within the realm of 60-degree math, a departure from the traditional Euclidean framework becomes evident. The inherent symmetry in this mathematical context introduces rotational symmetries of 60 degrees, leading to a distinct discretization of transformations. Unlike the rigid motions and scaling operations typically associated with parabolic transformations, the symmetry transformations necessitate a deeper understanding of how the parabola's curvature interacts within a hexagonal lattice framework. Describing the parabolic shape relative to a coordinate system based on equilateral triangles or hexagonal tiling proves essential in this scenario. The impact of 60-degree symmetry on parabolic shapes within hexagonal systems can be significant. Unlike their behavior in Euclidean geometry where they can be easily transformed into the standard form y equals x caret 2 / through scaling, parabolas in this context may appear segmented or fractured due to the inherent angular divisions associated with 60-degree symmetries. This unique perspective adds layers of complexity to the exploration of parabolic transformations in a 60-degree mathematical framework. Examining the relationship between curvature and angular symmetry is a key focus of this research, specifically how a smoothly curved object such as a parabola fits into a discretized, angular space. The constraints imposed by symmetry can result in a different visual representation of the parabola, often resembling piecewise linear approximations when viewed within a hexagonal grid. Application of these concepts to optics and reflecting mirrors is particularly intriguing. Parabolic mirrors, commonly used in telescopes, possess the unique ability to focus parallel rays to a point. When designing parabolic reflectors within a hexagonal symmetry system, it is essential to consider how the symmetry impacts the focusing properties of the parabola. In a 60-degree spatial context, the paths of light rays may deviate from those observed in Euclidean systems, necessitating novel approaches to achieve the desired focal points. In traditional Euclidean geometry, any parabola can be transformed into the unit parabola y equals x caret 2 /. However, in the context of 60-degree math, the concept of similarity undergoes a shift due to the constraints imposed by the underlying lattice structure. The universal applicability of the unit parabola may be altered, as the lattice geometry dictates different behavior of parabolas under the permissible transformations within 60-degree symmetries. In conclusion, the incorporation of 60-degree math into discussions on parabolas and transformations introduces a new framework that highlights hexagonal symmetry and angular constraints. This perspective shifts the traditional view of smooth and continuous transformations of parabolas in Euclidean space to one that is influenced by the discrete and angular nature of 60-degree math. This opens up opportunities to explore how geometric concepts adapt when applied to non-Euclidean spaces governed by different symmetries, such as those found in hexagonal lattices or 60-degree rotations. The amalgamation of geodetic mathematics and quantum methods offers a unique approach to complex concepts like quantum tunneling and the holographic principle. By integrating these two frameworks that focus on different constraints and symmetries, curvature, space, and quantum interactions, we can explore the following implications. Geodetic mathematics and curved spaces. Geodesy, focused on the geometry of curved spaces like the Earth's surface, extends to any non-flat surfaces. Geodetic mathematics acknowledges that the shortest distance between 2 points follows a geodesic curve that aligns with the surface's shape. When combined with quantum methods, geodetic principles can model energy barriers as curved, nonlinear spaces. This approach aids in visualizing the probability of quantum tunneling, where particles navigate paths through curved geometry. Geodetic paths serve as optimal routes, enabling particles to overcome barriers in ways not foreseen by classical physics. Quantum tunneling and curved geometry. Quantum tunneling is the phenomenon where particles can traverse potential energy barriers despite lacking the necessary energy in classical terms. By utilizing geodetic mathematics, we can visualize these barriers as curved spaces and pathways that enable particles to navigate around conventional constraints. Applying geodesic principles to tunneling can elucidate the most optimal or direct route, albeit curved or nonlinear, that particles follow through these barriers. Drawing a parallel to 60-degree mathematics and hexagonal symmetry, it becomes apparent that certain controlled systems, like materials with hexagonal lattice structures, may have their quantum tunneling behavior influenced by underlying geometric symmetries. Holographic principle and geodesic pathways. The holographic principle posits that all the information within a 3D space can be condensed into a 2D projection on its boundary, akin to how a hologram functions. This principle aligns harmoniously with the curved surfaces of geodetic mathematics, as curved geometries can be encoded in lower dimensional boundaries, resulting in a more concise representation of the entire spatial volume. The integration of geodetic mathematics with the holographic principle unfolds when we employ geodesic paths to describe how information is encoded on these boundaries. This approach enhances the efficiency of representing intricate quantum information. The introduction of hexagonal symmetries from 60-degree mathematics further impacts the distribution of this information, potentially optimizing processes like data transmission or quantum states. The integration of 60-degree math and quantum symmetries delves into the realm of hexagonal symmetry, a fundamental concept in modern physics with applications in materials such as graphene. Hexagonal arrangements impose constraints on transformations and similar triangles, influencing the evolution of systems within this geometry. In quantum systems, these symmetrical constraints impact quantum states, particle behaviors, and wave functions, compelling them to adhere to the angular restrictions of 60-degree rotations and reflections. This influence extends to quantum tunneling, where hexagonal symmetry dictates preferred tunneling paths based on the internal geometry of the system. Viewing the transformation of parabolas through hexagonal geometry has implications for the propagation of energy and information in quantum systems. The underlying symmetry naturally shapes the curvature of space and geodesic paths, leading to efficient routes for the evolution of particles or quantum states. From a scientific standpoint, the merging of geodetic principles and quantum methods offers a framework that combines geometric elegance with the uncertainty of quantum mechanics. This fusion could shed light on optimal paths for quantum particles, information encoding and retrieval, and the manipulation of quantum tunneling in materials with hexagonal symmetries. By leveraging these natural constraints, advancements in quantum computing and data transmission optimization may be achievable. Title: Integrating Synthetic and Analytic Geometry for Quantum Systems. By integrating both synthetic, involving triangles and constructions, and analytic, utilizing equations and algebra, approaches, we can approach quantum system problems from a multidimensional perspective. The inherent geometry imposed by natural symmetries in quantum systems, such as hexagonal symmetries, is just as crucial as the algebraic relationships between quantum states. Hilbert's axiomatic geometry combined with Artin's geometric algebra aids in unifying these perspectives. Modern computational tools now allow us to revisit historical problems like the parabolic mirror problem faced by Newton, using quantum principles and geodetic transformations aligned with 60-degree symmetries, to model and optimize optical systems like telescopes. The fusion of geodetic mathematics and quantum methods offers a new scientific framework for exploring concepts such as quantum tunneling and the holographic principle. This approach reveals how curved geometries, optimal paths, and underlying symmetries interact to influence particle behavior, information encoding, and transformations. This integrated approach not only provides deep theoretical insights but also practical applications in fields like quantum computing, materials science, and optics. By delving further into these intersections, we can uncover efficient solutions to complex quantum problems constrained by geometry. The connection between hexagons and cubes in 2D and 3D geometries underscores the significance of the holographic principle in quantum systems. The concept of a hexagon in 2D mirroring a cube in 3D illustrates the projection of a complex geometric object onto a simpler plane. This analogy is akin to the holographic principle in theoretical physics, where all the information within a 3D space can be encoded on its 2D surface boundary, much like how a hexagon represents a cube in 2D. In quantum systems, hexagonal symmetry, such as in the lattice of graphene, serves as a natural organization that simplifies particle behavior and wave functions. By applying the notion of projecting higher dimensional structures onto lower dimensional surfaces, this symmetry becomes essential in encoding information in quantum states. This approach allows for a more accessible understanding of complex quantum systems through a holographic mapping onto 2D systems, reflecting the principles of the holographic principle. Implications for quantum tunneling and information storage. The hexagonal geometry that naturally appears in physical systems such as graphene plays a significant role in influencing quantum particles' movement through materials exhibiting quantum tunneling behavior. These symmetries have the potential to provide valuable insights into how information can be efficiently represented. If we consider a cube in 3D as a representation of a complex quantum state, then a hexagon in 2D could serve as a compressed and simplified version of that state. This approach offers a more efficient method of encoding and retrieving information about the quantum system. The relationship between a cube in 3D and a hexagon in 2D elegantly reflects the holographic principle, which involves projecting higher dimensional data onto a lower dimensional surface. In this context, the hexagon acts as a simplified representation of the more complex cube, mirroring how the holographic principle suggests that vast universal complexity can be encoded on lower dimensional surfaces. This understanding deepens our insights into space, time, and quantum mechanics. The concept of as above, so below beautifully encapsulates the interconnectedness between the holographic principle and the geometric transformations discussed. This unity in creation reveals that complex higher realities can be reflected in simpler lower dimensions. This parallels the Quranic belief that the signs of Allah's creation are present both in the heavens and the earth, highlighting the unity and interconnectedness of all things in a profound and meaningful way. The concept of as above, so below emphasizes the interconnectedness of the macrocosm and microcosm, highlighting how elements in the universe reflect those on Earth and vice versa. This idea underscores the governing nature of Allah's will over all aspects of existence, from the smallest particles to the vast cosmic entities, all intricately linked through geometric principles by His divine plan. As stated in the Quran, we will show them our signs in the horizons and within themselves until it becomes clear to them that it is the truth. This revelation, achieved through the exploration of scientific, geometric, and spiritual realms, deepens our reverence for Allah's wisdom and flawless creation. This emerging field, known as quantum geodetics, merges geodetic mathematics with quantum methodologies. It intertwines the curved geometries of geodetic science with the probabilistic and wave-like behaviors of particles at the quantum level. This innovative approach allows for the investigation of particle behavior in curved spaces, holographic information encoding, and the role of symmetries and transformations in shaping reality. Quantum geodetics is aptly named for its combination of quantum, reflecting the probabilistic and wave-like nature of particles at the smallest scales. Geodetics, centered on the study of curved spaces, geodesics, and the role of geometry in movement and optimization, connecting to Earth's mathematical framework. Through the integration of these disciplines, quantum geodetics can study quantum tunneling across curved surfaces, evaluate optimal paths, geodesics, in the context of quantum probabilities, utilize the holographic principle to investigate information encoding on boundaries, analyze the symmetries and transformations governing diverse scales of structures and quantum systems. This new scientific framework would bridge the macrocosmic and microcosmic realms, potentially unlocking deeper insights into both cosmology and quantum physics, while aligning with divine wisdom of unity within creation.
A'udhu billahi minashaitan rajim. Bismillahir-Rahman-Rahim. Juggalos and thuggalettes, we walk with angels. In front and behind, they roll deep with the fago. But God ain't gonna change the game unless we change our heart. Ain't no runnin' when the punishment starts. Ain't no protector when the curtain's pulled apart. Yo, you see how the clowns before got wiped out? Firm on the earth, rain pourin', rivers flowin', no doubt. We set 'em up real high, but they fell real low. Sins too heavy, they lost the show. We told y'all stories of them wicked towns. Messengers came through, but they laughed like clowns. God sealed their hearts, they couldn't hear a thing. Now look at 'em burnin' in the hellfire ring. We gave the weak the land east and west. Made Pharaoh crumble, his whole empire wrecked. How many times we seen evil get crushed. When they see the storm comin', they all rush. Tryna escape, but nah, face the mess. Woe to us. We was wrong, now we confess. But God ain't playin', and the clock's tickin' down. On that day, they gone, wish they hadn't clowned. Juggalos and thuggalettes, we walk with angels. In front and behind, they roll deep with the Fago. But God ain't gonna change the game unless we change our heart. Ain't no runnin' when the punishment starts. Ain't no protector when the curtain's pulled apart. Y'all called to ride for God's cause, but you stingy. God don't need you, but you in need of mercy. Turn your back, he'll replace ya, quick as a snap. A new crew who ain't 'bout to fall into that trap. The clock's windin' down, Gog and Magog breakin' loose. Swarming down, breakin' barriers, no excuse. When the truth hits, they eyes wide, cryin' in disbelief. Woe to us. Too late to feel grief. We gave Moses the book, gave Mary a sign. A spring in the hills, pure and divine. Your religion's one, don't trip on that. But they split into factions, each wearin' a hat. Now they sittin' in confusion, lost for a while. Thinkin' their stacks and kids make life worthwhile. Nah homie, they don't get it, they lost in the chase. The real winners? The ones seekin' God's face. They do good, they tremble at the thought of that day. When they meet their Lord, every soul gotta pay. Don't cry for help, that time is done. Revelations were told, but you turned and run. Juggalos and thuggalettes, we walk with angels. In front and behind, they roll deep with the Fago. But God ain't gonna change the game unless we change our heart. Ain't no runnin' when the punishment starts. Ain't no protector when the curtain's pulled apart. Whoop whoop.